Okay, so let's solve problems involving rates of change. So let's go with an example. Say we have a Ferris wheel. Let's pretend that looks like a Ferris wheel. And say that we have the elevation from the ground to any given point at where a certain person is. So let's say I am on this Ferris wheel and I'm here. And we're going to say that h of t is going to represent the height above ground in meters, where I am, and t is going to be time, and the function that's going to represent my height is going to be 5 cos 4 t minus 10 degrees plus 6. It's going to be a cos wave because I am going up and down. So we want to see at what time, at what exact time. Say we're going to take an educated guess and say at 55 seconds. I will be closest to the ground at here, and we're going to try to prove that or check it or see if that's true. So what we're going to do is, instead of 55, we're going to look at 54 to 55, because basically when we look at the rate of change at these two, if we have a rate of change that is going at a decline like this or an incline like that, you're going to have a proper number, like a number that's going to be really positive or really negative. But at the very bottom, you're going to have a line that is a rate of change that is very close to it's going to be like this. That line, the tangent line, is going to be 0. Or, yeah, 0. So, let's look at the delta here. So we have h at 55 minus h at 54 over 55 minus 54. So if we plug in 55 into this in a calculator, we should get 1. And if you punch in 54, you should get 1.0122. Then you divide that by 1, you get negative 0.0122 meters per second. Because remember, our numerator is in meters, because h of t is the height in meters, and t is in seconds, so we are doing meters per second. And now we're going to do the exact same thing with h at 56 minus h at 54. And that is going all divided by 56 minus 55. So let's just put a line here. That's going to be 1.0122 minus 1 over 1, which again is going to give us 0.0122. So what do we know now? That based on this information, at 56 you're going to have 1.0122 meters above the ground. So if you had it like a like the bottom of the Ferris wheel. This is 1 meter above ground at 55 seconds. At 56, it'll go back up slightly more. So this is going to be 1 meter, and then this is going to be, at 56, it'll be 1.0122, and then at 54, it'll be right here, the same as 56. It'll be 1.0122, and there you go. So basically, the rate of change that we've seen from here to here is negative, and the rate of change from here to here is positive. But if we did a rate of change from here to here, you'd have 0. So it's not unwise to say that the lowest point will happen between 54 and 56. So 55 would make a great estimate and therefore would become the lowest point. So let's look at one more example with the rate of change. So let's say we have f of x equal to x squared plus 4x minus 21. And we want to see that, or prove that at x equals negative 2, that's where the minimum point happens. So we know that this is a parabola with a positive in the front, so it's going to be like this somehow, somewhere. I don't know exactly where, but it's going to be opening upwards. So let's find or prove that x equals negative 2 at some point. So the way we're going to do this, we're going to estimate the slope of the tangent to the curve at when a is equal to negative 2 by writing the equation or an equation for the slope of any secant line of the graph f of x. So we're going to write the slope is equal to the function of negative 2 plus h minus f of negative 2. So we're going to basically say that h is going to represent a small amount of difference from the negative 2, and we're going to find the delta from there use that point and the difference from there to find a slope of a tangent line. So to find or to estimate the slope of the tangent line at x equals -2. Well, this is why it's going to be somewhere here. Let me just correct that. Let's put this somewhere. I don't even know there. At x equals -2, we're going to use 2 points and the difference quotient. So for 1 point, we're going to use this. Well, actually, we're going to use -2, -25. So let's put that there. So with that point, and then we're also going to use another point which is going to be generic. So that point that we're going to be going towards is going to be -2 plus h, the x coordinate, and then the y coordinate is going to be the f of that. I hope it's not super confusing. But once we plug it into our slope formula, it'll make sense. So when you plug these two numbers in, you're going to have something like this. Let me put that somewhere else. And now when we simplify this, well, this is all still over h. So when we simplify this, we're going to get we should get 4 minus 4h plus h squared minus 8 plus 4h plus 4 all over h. So the plus 4 and minus 8 will cancel out. The -4h plus 4h will cancel out, leaving us with h squared over h, which is just h. So if we were to use a very, 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 very small value here, so all we've done so far is prove that we can use h as a small increment here. So we know that the slope at where like all we've done so far is prove why we can use a variable h to use an ambiguity to say that the tangent line is going to be close to 0. The slope will be 0, so we can say that h is going to be so small. It'll actually become say we do the delta of these two rates, so we can have 0.01 plus negative 0.01 over 2, and we're gonna have, basically this is gonna cancel out and give us 0. By that logic, using 0.01, we can prove this, that at f at negative 2, you have negative 25, correct? But if I add 0.01, I'll get, well, that's not 0.01, that's 0.1. I should get negative 24.99 if I plug it into this formula. And if I go over f at negative 2.1, I'll also get negative 24.99. And there you have the difference. That h value that we were looking for. So this one and that one, they're off by 0.01. Which was our h value that we used. So we can say that because the tangent line that we introduced, since that is equal to 0 when x is equal to negative 2, and also since the values just around f at negative 2 are greater than the value at x equals negative 2, our minimum occurs right here at x equals x equals negative